I want to make a clip, and sorry for the background noise, that it would describe more or less what I published, and making a reasonable comment on writing at least some algorithms in Java or in C# that they could run faster than a C++ code. And for people that have this view, or they don't have it, but they think people don't say it, this is this guy Patrick that says that if you write in C++, the code will be easily beaten, will beat any Java code out there. And this is really interesting to hear it because, for example, there is a paper which I was publishing on, and I was putting it even in the description, that it was written the same algorithm in C++, Java, and Go. And what it does is that you have this DNA building machines and gives to you huge files that name sum or bam, 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 and it tries to create with elPrep algorithm as many tasks to run on big machines. So if you have 100 cores or at least 64, it would run properly. And then it will load all the data in memory, and some algorithm required to be in memory. That's the trick for this algorithm to work fast. And then it does the processing, and then it writes down to disk. So the paper is there. There is a source code of the algorithm, at least at that time. And the critical part we should understand is that what it's used. So there is tens of gigabytes of data, as we said. Some just to read this data, it can take some time on slower machines. They were mitigating it with the NVMe disks, but my paper and my machine didn't have an NVMe disk. Then it creates many tasks. For the Go language in particular, they had to create their own version of streams or thread building blocks in C++. Then, because it keeps all this 10 of gigabytes in memory, or hundreds in original paper, they would rely on memory allocator. They tested more allocators and they keep the best number for C++. But it will be even worse if they were just using the default. Java was using the default algorithm, but because they noticed it was done run fastest, and for their metrics, and Go was the default GC. And the compiler optimizations may matter, but they were not the big thing, because you split a string quickly, but when you allocate, the allocating of the strings would be expensive, in my understanding. So first of all, for people who care, they because the allocator was a big bottleneck, they run with the default implementation with 16 minutes, almost 17 minutes was using the default memory allocator. But if you work and use a faster one, you get to 10 minutes with their input data set and 255 gigabytes of memory usage. But based on their metrics, that was the best they needed. They could spend a bit more extra memory, but they would have a faster allocator. So Java, let's be clear, with the default values, it is already much faster. So let's go back. We talk about 10 minutes, 23 seconds versus 7 minutes, more or less, on their data set, but it uses, let's be very clear, much more memory, 335 gigabytes. And this is what's the summing. So Go, it's on the left, most, middle is Java, C++, it's right, and if you see on the time, Java is clearly the fastest. It's a bit under 7 minutes. Also, on the, if you multiply the memory usage with runtime, Java still beats C++ with the best allocators they tried. So my paper, what I published, it was that I noticed that the Java implementation in particular looked a bit worse. I definitely don't think malpractice in the original paper, but it looked to me that some parts were not even measured properly, or they measured the allocator but not their algorithm. And when I did with the profiler, basically if you put just 350 column, so you'll improve a lot your algorithm. So in their score, even the memory remains the same, the runtime it almost speeds up by a factor of 50% or something. So and it would be the Go implementation, which was in the original paper. So if you see 3 columns for the original is their Java algorithm, buffered is the 350 there, and it has a reason. It depends on this bell curve distribution, things like that. But it's more important, and also because Java has an extra loss in runtime is, but you'll see it's quite small, is that Java strings are not, they have to keep a bit wider byte set, because in Go strings are UTF-8 and in C++ strings are UTF-8, and Java is the only one with fat strings. So I was using byte arrays, so you can make it even faster. So just to be very clear, this is exactly their own algorithm with very small changes. And then I suggested, just for the runtime sake, so imagine the 120 seconds, 2 minutes runtime to scale, because I didn't have as big machine as they do. It would be basically the 7 minutes. So buffered would reduce to around 60 seconds, as you can see, and you can work still a lot and reduce a lot allocation and how garbage collection cost works to do it to almost a factor of 5 or something like that, from 120 the original algorithm to compact or compact parallel. And they would use some techniques. Please read the paper. If you have unclear things, please contact me. I'm happy to answer on the paper. But what I would be clearly doing is that I will store the data in a garbage collection friendly way, which is named column store. I would be using compacting, so I would remove kind of duplicates or keep a letter of DNA sequence in 3 bits, something like that. But you don't have to care about this if you don't care. But just to say, you can do simple techniques and you can improve a lot the runtime. And if you do something which is named parallel prefetching, so as you do processing, you read in advance on another thread, you can do this compact par runtime. So it's really talking to scale that 7 minutes, it will be kind of 1.5 minutes probably on the original paper if my algorithm would be used. Maybe I missed something, but this is beyond the point. You can have definitely a factor of 2. And if you take also memory, this compact and compact parallel, they were very friendly on memory. They would really do the compacting, they use much less memory. They would speed up. And to be very clear, if C++ algorithm will have speed ups, but not on the same scale. So I did also a .NET Core implementation, but I didn't publish it. And you can do even maybe by a factor of 2 on top, or maybe 1.5. And the main and the hot item why it's so fast, it was I could put it for 2 reasons. I could use structs meaning I will remove some allocations, even for one splitting strings or things like that. And the dictionaries which I rely to do the memory compaction or hash map for Java folks, I can precise it. So just to know the algorithm, my algorithm, I'm not claiming it's optimal, but if you have a factor of 5, it's not a big thing with factor of 10. But also, to answer the original comment, if you rewrite it in C++, it will not become much faster, because as noticed even in the original paper, is that the allocators is the biggest bottleneck, at least for C++. And both C# and Java use what is named bump pointer allocations. or arena allocators. And the cost of Java, it will be how much garbage you throw away and which structure you use. And this is what C++ was sucking. Just to say clearly, the allocator is not optimized for C++ for very short allocations, which C# or Java they do. Also, the C++ runtime probably has a benefit of parsing, but it's really hard to beat in general. I think it's maybe 10% faster, let's say. So if you write it in C++, that part, but that part of runtime is not even 10%. Maybe it's 10% of runtime. So, and the last part, if you compare at least with the C# implementation, the unordered map, at least by default, doesn't have a precise function or value in constructor or reserve. And if you have this, probably again you'll remove many hidden allocations and reduce the allocator's cost. But not having all these things will make the discussion clear. Okay, so thank you if you listened. Thank you if you didn't listen. But that was my paper about, and at least in some domains, just rewriting a code from C, everything to, let's say, from C# to C++ will not make it faster. And I have also this experience at work when really some people rewrote my code in C++ because they thought that's the issue. And yes, it was using less memory, but it was 80% of the speed of my code. And I'm not judging these particular developers, but this one is just measure it and prove it for yourself. And if you prove me wrong, please give to me a linked paper, publish it, and show to me that I'm wrong, and I will be very glad to be wrong. Thank you.